Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at differentiation. So what is differentiation? Differentiation essentially is an operation that we apply to a function to get another function. So let's define it. So we say differentiation. Let f of x be a function. Should say suitable in brackets. All the functions we'll see on the A-level syllabus will be suitable. Be a suitable function, then its derivative, namely f prime x, is also a function which is obtained using the following definition. So what is the definition? Well, we start with the function f, we evaluate it at some point, which we label x plus h, and we subtract from it the same function f, but evaluated at another point, f of x, and we divide the whole thing by h, where importantly h should not be 0, because otherwise that division is not defined. And once we've got this fraction, we effectively take a limit as h tends to 0. And this fraction on the right-hand side, no less, will actually give us a function in its own right once we've evaluated the limit. And that function we label as f prime x, which is the derivative of x. So what is differentiation? It's a process by which we go from a function which would be, for instance, f of x, to a function which would be f prime of x. So differentiation was actually invented simultaneously by two different people, the first being Isaac Newton and the second being Leibniz in Germany. Because of that, for historical reasons, there are lots of different notations that get used. So the one we defined above would what would be conventionally be called as the Newtonian description. So if f of x is a function, let me say if f of x is a function, then f prime x is its derivative. This is obviously the Newtonian description. But the Leibniz description is as follows. So if y equals f of x is a function, then dy by dx, which obviously is the exact same thing as f prime x, is its derivative. Both these notations are very, very common, and most textbooks will use them interchangeably, so it's good to know about these. So what is differentiation good for? Well, it's good for lots of things, but let's focus on one in particular for now. Let's think about trying to work out the tangent to this curve at the green point here, x, f of x. So how would we work out tangents? Well, we need to work out a straight line, and a straight line's got to have a gradient. So we need to know the gradient of the line, and we need to know the point at which it's passing through. But the point at which it's passing through is clearly x, f of x, or in other words, xy, where y is f of x. So that's easy enough. So now the slightly hard part is actually working out a gradient. And this is where differentiation starts to help us. So how do we work out a gradient? We take the green point and the red point, and we effectively consider a triangle going between them. And we look at the gradient by looking at the change in y and comparing it to the change in x. So what's the change in y? Well, it's going to be the f of x plus h take away the f of x, and what's the change in x? Well, the change in x is going to be x plus h take away x. And of course, this is nothing other than the fraction that I wrote down earlier in the definition of differentiation. And we can see what's going to happen as h becomes smaller and smaller and gets closer and closer to zero, but it will never actually be equal to zero, because otherwise this thing on the top is not quite then defined. It will never be equal to zero. But as it gets closer and closer to zero, we end up with this limit process. And indeed, this limit process is precisely what we have defined as the derivative at the point x. So what does differentiation help us do? In fact, differentiation is very useful because it helps us to work out the gradient of a tangent passing through a generic point x, y, or x and f of x. So let's consider an example. Let us try and work out the derivative of the function f of x equals x squared. So we start with the definition, obviously. We want f prime x, and it's defined to be this limit as h tends to 0 of f of x plus h, take away f of x, and we divide the whole thing by h. Now in this case, f of x is x squared. So here the function f is being evaluated at x plus h. So I'm going to have x plus h squared, and I'm going to take away the function f of x, which is obviously x squared, and the whole thing is divided by h. And the limit would obviously be there. We apply the limit right at the end, but we keep writing it down as a matter of mathematical convention, standard notation. So let's expand the numerator. So the x plus h squared term is going to give us x squared plus 2hx plus h squared. And obviously we take away x squared, and the whole thing is divided by h, and the limit is still ever present. Quite straightforwardly, we can see that the x squareds are going to cancel. So what we end up with is this limit as h tends to 0 of 2hx plus h squared, and the whole thing is over h. But of course, we can tidy that up a little bit. So we still have a limit that we're considering, but we can factorize out the h. So we get that, and the whole thing is divided by h. But again, in this case, because h is not actually 0, the h's are going to cancel. So what we actually end up with is we end up with a limit as h tends to 0 of 2x plus h. Well, what happens to this? Let's think about what happens to this thing on the right-hand side. Clearly, as h gets closer and closer to 0, the function 2x plus h is going to get closer and closer to just 2x. So in this case, what we figured out is if f of x is actually x squared, then the derivative of f of x, or the function you get when you differentiate f of x, is actually going to be 2x. So let's think about another example. In this case, we have to work out the gradient of a tangent line to the curve y equals x squared at the point 2, 4 on the curve. So we've already seen that differentiation effectively gives us a function, and one way to interpret that function geometrically is that the function would tell us the steepness of the tangent line at the curve at a particular point. So let's try and use that. So take f of x to be the function y equals x squared. So in other words, f of x equals x squared, right? Then we've shown in the first example that the derivative of that is actually going to be 2x. But we also know that the derivative at the point x actually gives us the gradient of the tangent. Of the tangent at point x, y to the curve y equals f of x. So in this case, we'd simply take x to be 2, and what we get f prime of 2 is actually equal to 2 times 2, which is actually 4. So the tangent to the curve y equals x squared at the point 2, 4 will have gradient 4. So the next example requires us to show that the gradient of a straight line is always a constant. In other words, it's going to be the same regardless of which point you take on the line. So let's start with a generic line. So take y equals mx plus c as a generic line. We want to be able to describe this as a function. So we can say y equals f of x, where f of x is actually mx plus c. And now what we want to show is, because we know differentiating a function gives us another function, the derivative, which actually tells us information about the gradient. So let's take this function f of x and try and differentiate it. So we want to work out f prime x, and of course we would do that by taking the limit as h tends to 0 of the function evaluated at 2 points, subtracted, and then the whole thing divided by h. So in this case, what is f evaluated? If f evaluated at x plus h, well, it's m x plus h plus c. That's f evaluated at x plus h, and f evaluated at x is just mx plus c. And the whole thing, of course, is divided by h. So in this case, we still have the limit. And if we tidy this up with a bit of algebra, we get mx plus mh plus c minus mx minus c. And the whole thing, of course, is divided by h. So things are going to cancel, of course. This mx is going to cancel with that mx. And thankfully, the c is going to cancel with that c. So what we end up with is we end up with a limit as h tends to 0 of m over h. But since h is non-zero, by the definition of differentiation, we know that we can just cancel out the h's in their own right. So what we actually end up with is m. And of course, m is a constant, so I should have said that here, where when I defined y equals mx plus c, where m and c are constants. And because that's the case, so what we've just shown is we've shown f prime of x is a constant, which is precisely what we were required to show, that the gradient is a constant. We've worked out the gradient. We've shown that the gradient is actually m, and it is indeed a constant. This should actually be reassuring, because we were always told that the m here in y equals mx plus c is the gradient of a line, and in this case we have been able to show that, but also we've been able to say a bit more. Moving on to the next example, let's try and figure out the derivative of the function f of x equals x to the n. So again, we will just apply the definition of differentiation. So we want f prime x, which is going to be the limit as h tends to 0 of f of x plus h, take away f of x, and we divide the whole thing by h. Now, in this case, we're going to have to figure out what the expression f of x plus h would actually look like. That would, of course, be, given the description of the function, it would be x plus h to the n. That, as it stands, is going to be quite awkward to be able to deal with. So we're going to have to expand this using the binomial theorem. So let's do that quickly on the side here. The binomial theorem, of course, uses Pascal's triangle numbers, which we can write in a very compact way using this sort of notation. Another way of writing it is n choose r, of course. So in this case, we're going to get n choose 0, x to the n, h to the 0, plus n choose 1, x to the n minus 1, h to the 1, plus n choose 2, x to the n minus 2, h to the 2, and it's going to carry on, and we're going to get all the way up to n to the n minus 1, x to the 1, h to the n minus 1, and lastly, n choose n, x to the 0, h to the n. Now, if we think about what are we going to get when we do x plus h, f of x plus h take away f of x, well, I should say at this stage that this number here would just work out to be 1 by the definition of n choose r, which I'll write here. N choose r is obviously n factorial over r factorial n minus r factorial. So if we actually do that calculation with the thing highlighted in blue, we'll actually just get 1. So we end up getting this sort of thing, n1 x to the n minus 1 h plus n2 x to the n minus 2 h squared plus all the way to nn x to the 0 and then h to the n, and we obviously take away x to the n. But the beauty here is the x to the n will cancel with the x to the n at the front. So now that we have this, we can actually go back to our definition of differentiation, which is obviously here, and we could substitute the expressions we found for the numerator. So f prime x is actually going to be equal to the limit as h tends to 0 of all this thing in the numerator, which is n1 x to the n minus 1 h plus n2 x to the n minus 2 h squared plus all the way to nn h to the n. And of course, in this case, we need not actually worry about exactly what the coefficients are going to give us, because you'll see most of them are going to go away in the end. Obviously, the whole thing here is divided by h. Now, this is really, really useful, because what we can actually do is, if we take a more closer look, we've actually got a h in each term. We've got a h there, we've got at least a h there, and so on and so forth. The powers of h are only going to go up, and they're going to go up to n, right? I should have said at the beginning where n is actually a natural number. So n is some natural number. So the powers of h are actually going to go up to n. So what we can actually do is we can factorize out a h. So let's do that. So we've got n1 x to the n minus 1 plus n2 x to the n minus 2 h plus all the way to nn h to the n minus 1, and here comes the factorization, which is a h. So I've taken a h out from each term, and obviously the entire fraction is going to look like so. And now we can cancel these h's, because by definition of differentiation, the h was never taken to be 0 in the first place. So since we've got that, let's make a bit of room here. What we actually end up with is we still have this magnificent limit, but now we don't have a denominator. We just have a numerator. So things are looking a lot nicer. nn h to the n minus 1. So now let's have a think. The limit is going to apply to every single thing inside that big bracket equivalently. And each term, other than the very first term, actually will have or has a h in it. So what we're going to see is we're going to see every single term which has a h in it, which is there, and all the terms in between actually, they're all going to go to 0, because h is going to get smaller and smaller and smaller thanks to this limit. So what we're going to end up with is we're going to end up with n1 x to the n minus 1 plus 0 plus dot 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 plus 0, which of course will just give us n1 x to the n minus 1. Now all that is left to do is to be able to expand this Pascal thing. So we've got n factorial over 1 factorial over n minus 1 factorial multiplied by x to the n minus 1. But of course n factorial is just n times n minus 1 times n minus 2 and so on, which we can re-express as n times n minus 1 factorial. And the whole thing is just over n minus 1 factorial, because 1 factorial is just 1. And the x to the n minus 1 is still there. Now at this stage, we can cancel out the n minus 1 factorial because these things are non-zero. So given that's the case, I basically end up with x to the n minus 1. And this is the result we were looking for. So if we've been able to show that when I actually differentiate my function, x to the n, I get nx to the n minus 1. As almost a final thing in the video, let's look at some basic properties of differentiation. There are two key properties. The first one is if I define a new function called capital F of x, and I define it by taking two functions, f of x and g of x, and by adding them up, then if I want to differentiate my function capital F of x, the property tells me that I can just differentiate it by actually differentiating the lowercase f of x and the lowercase g of x and adding them up. The second property is, suppose that I define a function capital F of x, not by adding up two separate functions as I've defined above, but say by taking a function lowercase f of x and multiplying it by some constant number a, where I can say a is a real number in brackets, then how would I work out the derivative of f of x, capital F of x of course? Well, the property tells me is the a has no part to play in this process. I simply differentiate the lowercase f of x and multiply that by a to be able to get the derivative of the uppercase f of x. Let's have a think about why these properties may hold. And of course, we go back to just a definition of what a derivative is. So let's consider the derivative of capital F of x. It's obviously going to be the limit as h tends to 0 of f of x plus h, take away f of x, and the whole thing is over h. Now, by definition of f of x, this is capital F of x, of course, we have the following. And just to make this very clear, let's put some brackets in. And the whole thing is divided by h. But now by basic rules of algebra, the fact that I can add things in different orders and the answer is not altered, I can move the sum around. So I can say it's f of x plus h, take away f of x plus g of x plus h, take away g of x, and of course the whole thing is still over h. Now, the limit, of course, applies to the whole thing here. Again, if I massage this a little bit more, because order of summation does not matter, I can actually go further and say this. And of course, the whole thing is divided by h. I'll write that in a slightly awkward way. Let's make a bit more room. Now, this statement can now be massaged in a way to get something really nice. So I can say f of x plus h, take away f of x over h, plus g of x plus h, take away g of x over h. And this is, of course, nothing more then an algebraic statement of the form a plus b over c is equal to a over c plus b over c, right? That's precisely what I've done. I've taken that part there, and that's behaving like an a, and the other part here is behaving like a b, and the h is behaving like a c. So I can split it up like that. But since the limit applies equally to everything in the brackets, I can actually apply the limit individually to each part. As follows. And of course, now where we are is we can basically use the definition of a derivative again, because it's pretty clear that this thing here is actually going to be the derivative of g, and the other thing here is actually going to be the derivative of f. So it's going to be f prime x plus g prime x. And this is, of course, exactly what the property 1 told us that we could do. Let's have a think about property 2. So in this case, we redefine our f, capital F, of course, to be a f of x, where a is some real number, it's of course a constant, right? We want to figure out f prime x. Well, let us go back to the definition of a derivative, which of course is f of x plus h, take away f of x, of course, capital F in both cases, and the whole thing is divided by h. But as we've defined capital F above, it's defined in terms of lowercase f. So we actually resort to that definition, and we arrive at this fraction here. Now, the interesting thing here is, of course, that the number a plays no part in this limiting process. And because the normal laws of algebra apply, these are just numbers at the end of the day, I can take the a out and I can rewrite the above expression as follows. Now, this is something a lot nicer, because the thing on the right-hand side, which I should, just for clarity's sake, show, this thing here is nothing more than the definition of a derivative. So by the definition of a derivative, I can say that thing is f prime x. But again, this is precisely what the claim of property 2 was, which is if you have to differentiate the capital F, and the capital F is obtained by taking some function lowercase f and multiplying it by a, then the derivative of capital F is obtained by taking the derivative of lowercase f and multiplying it by a. So finally, it's worth just thinking about what we've seen in this video so far. So what we have seen is we've seen the definition of a derivative. And from that, we have seen examples of being able to calculate derivatives. We've seen a geometric interpretation of derivative. And we've also seen some basic properties of derivatives. Lastly, what I would say is, suppose we have a function which is quite complicated, which is, say, as an example, say something like 5x to the 9 plus 27x to the 4 plus 3x squared plus a half x plus 2, for example. Then given the property that we've seen already, which is if you've got a function like f of x is actually made up of two functions, say in this case h of x and g of x, then the way to differentiate f of x is to differentiate each part of the function on the right hand side. Then what we can basically do is, using that property, we can actually just write down the derivative of this thing here, because we know that when we have a function like y equals x to the n, we showed that the derivative of that was actually going to be nx to the n minus 1. So using this fact together with this property, what we can actually write down is the derivative of the function above is just going to be 5 times 9, which is 45, x to the 8, plus 27 times 4, 108, x cubed, plus 3 times 2 is 6x, and the power of x is x to the 1, obviously, so a half times 1 is a half, but you subtract 1 on the power, and that's 0. And 2 can be thought of as 2 times x to the 0. So you multiply by 0, so you actually just get 0, and it doesn't really matter what the power is, because whatever you multiply by 0, you get 0. So that just goes to show that actually with some pretty basic properties and a clear definition, you can actually get quite far and start to differentiate things that are quite complicated. With that, I'd just like to say, we hope you found this video useful and want to see more. Do use the comment section to say what topics you would like to see more videos on. And of course, hit the like and subscribe button. Thank you for watching the video, and we'll see you in the next one.